Hello. See if I get the light a little bit better in here. That's not very helpful. That's not either. Oh well. So how's your week been, Jedediah? Welcome, welcome. How's everybody surviving the apocalypse today while you're on mute? Okay, this is going to be really annoying if I have to admit everybody into the thing. But I get the reasons. Because Zoom is not the best or most secure place to do this. All right, we got 5 of you here. Another minute to go. 6, 7. So I'll ask again, everybody else surviving the apocalypse well, or did we like lose half of our class to it? No problems with zombies out there?
Nothing our boy baseball bat can't solve.
Yeah, we've kind of just canceled 2020. We're going to skip straight to 2021. All right, well, let's go ahead and get started, guys. If any of your parents, again, have any questions on grading or how to deal with things, or if y'all have any questions, feel free. Do not hesitate to email, text. I may not get back immediately. Hopefully, I'll get back by end of day. I actually still fortunately have a day job I get to do 100% remote. So, you know, there's a bonus for that for my family at least. Anyway, whoops, more people wanting in. Whoops, click the admit button. Come on. There we go. So that is always open. Also, please remind your parents, I've sent out at least a couple of emails. If they're not getting emails from me, then also have them check with me. Tuesday night, 7 p.m., I'm on a Jitsi. I've opened up from 7 to 8 on Tuesday evenings to be available for help on grading and such. I'm assuming since we're going to be doing tests this coming week that will be a bigger thing. So try to get your tests done before Tuesday night so your parents can get the help grading it so they can get the grades in. Anyway, we moving on to module 14 review questions. Let's see if we can get through all these and we can cover miscellaneous stuff at the end if we have a chance, because it seems to take a little bit longer here than it does in person. And actually, if people want to jump in, let me see. I don't know if I can see the chat here or if this is just the participants list here. This may just be participants list. Let me see if I can get, or maybe they've disabled chat. They may have revoked our chat privileges, guys. Let's see. Nope, it's here. Now I see. Great, I can see it. Electric potential energy, are they the same thing? Why and why not? Who wants to jump in on that one real quick? As people rapidly hit the mute button so they're not being heard. I'm going to start picking volunteers. Hey, we got AJ coming back in. Just so we know who the late people to class are now, since I have to admit you to class. And another one. Maybe I should wait till like 12:05 to start class so that I can actually get y'all all admitted. All right. So electric potential energy, they are not the same thing. They do not have the same physical units. If something doesn't have the same physical units, then they can't be the same thing, is the first part of that answer. The other thing is they're just not the same things, whether they have the same units or not. They describe different physical phenomenon. Let's see. Number 2, a positive particle is near a stationary negative charge. Is the electric potential positive or negative? And so the first part, and there's another follow-up question, but anyone want to jump in on the chat or on voice and try to show us how smart you are, or take a risk at being, you know, not as well educated and learn from the experience?
The electric potential is negative.
The electric potential is negative. Why is that?
Where's
You are correct. The question is why.
It's negative because the electric potential depends on the stationary charge, and the stationary charge is negative.
Perfect. Exactly correct. So is the electric, what about the potential energy of the positive particle? Is the potential energy on the positive particle, the one that can freely move around, is that one positive or negative? What's the formula for electric potential? Okay, I have got to get rid of this mirroring thing because that's annoying.
It's the electric potential times the charge of the other particle.
That's the potential energy, right?
Sorry.
What is potential energy? Or what is the electric potential? Sorry, not potential energy. What's the electric potential? What's the formula for that?
K times Q over R.
Yep, hang on a second. Got to admit somebody else into the chat or into the here. There we go. Sorry, what was that again?
K times Q over R.
Correct. So that means potential energy is going to be K. Let's do it this way. Q over R, correct? So if we have a, what's the big one in this case is negative, and the little one is positive. Well, if that's negative, then the potential is negative. If we have a negative and a positive, what's potential energy? Positive or negative?
Owen said it was negative.
Owen says it's negative. Ah, yep. Okay, sorry. I see the chat now. So yes, because you have a minus and a positive, you multiply those together, you still get a negative. Cool. So let's move on to the next one. We are on number 3 now. A negative particle. So let's do this. A negative particle is near a stationary positive charge. So the big stationary charge is positive. The little one is negative. Same questions. Is the electric potential positive or negative? Try to keep an eye on the chat here. Electric potential is positive, correct, because it's the stationary charge determines that. Now, what about the potential energy? Let's go for the potential energy part of the negative particle. Potential energy on the negative particle. Is that going to be positive or negative? And that will be negative. We've got from Malachi, from lots of people. Awesome. Class participation all simultaneously. That's great. So yes, you're correct. So in this case, the potential will be positive, but the potential energy is still negative because that's positive, but that's negative. We still have a positive times a negative, so the potential energy itself is negative. Now, different scenario. I'll leave those equations up there. We have a D cell battery. It's a D, not that that matters, but it's rated at 1.5 volts. If a proton, okay, so this is the positive end, this is the negative end. We have a let's have a little wire that connects the two. If we have a proton, all right, fine, I'll get rid of the equations. We have a proton and it travels from the positive end to the negative side. What potential difference does it experience? Bueller. I've got a minus 1.5 volt.
Oh.
What else do I have? I've got a, oops, nope. Well, that's 1.5 minus. Decreases by 1.5. All right. Well, the 1.5 is absolutely correct. Now we got to determine, is that correct on a decrease? And I would say yes, because the 1.5 is the magnitude of the potential difference, and it goes from a positive to a negative. So this could be like 10 million 1.5 volts, and this could be 10 million volts based on something out here. But the difference is going to be 1.5 volts, and it's going from a higher positive level to the negative. So you are all correct there that said negative, 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 and decrease by 1.5 volts. Good job. Let's see, what's next? Where's the problem sheets? There we go. That's the end of the first page. Next page. 5, a negative particle is placed a certain distance away from a positive stationary charge. So let's draw the picture. This does not work as well to erase. I'll get rid of those for a minute because they take up too much space on my tiny little board. So we've got a negative particle. It is placed a certain distance away from a positive stationary charge. I'll draw it bigger to make it stationary. If the particle suddenly moves towards stationary charge, does it experience an increase or decrease in potential energy? Potential energy decreases. Well, let's figure this out. Potential energy is going to be K Q Q over R, or just QV, but V is KQ over R. So out here, we're going to, the only thing that's changing here is going to be R. We're going to go from R1 to R2 when it's, say, much closer in. So to start with, all that stays the same. We're going to have a negative number here, right? So the potential energy, and dividing by a larger R means that's going to be a smaller number. So I'm going to say that's going to be a negative, whoops, small amount of potential energy in the first scenario. In the, yes, you can still see this good. Potential energy in the second scenario is still going to be negative because it's a positive times negative. So this time it's going to be a negative, but it's going to be a bigger number because R is smaller on the bottom. So the numeric, sorry, the magnitude of it will be much larger. But since it's negative, it's going to be a smaller amount. It's going to be less actual energy, if that makes sense. So here, let's say, for instance, this might be -5. This could be end up being -10 as an example. So the energy actually decreases. Is that enough double negatives for people to work through to their English teacher with? This is where signs are important, magnitude is important, and understanding where we're at. So for instance, if let's draw, a hill like this where we have a little ball rolling on it. All right. So here the potential energy is greater. It's a bigger number. But let's actually do this, where there's the 0 mark. Up here, we might have, say, +10 joules of potential energy, whatever, of potential energy. Here we might have 0. I'll put joules, sure, why not? Just have units on here. Here we might have, when it's down at the bottom, -10 joules. So it's the same magnitude, but it is actually less potential energy for a ball rolling down a hill, if that helps, like, get it into the head a little bit more easily. All right. Because while these review questions are more simplistic than the other ones, the concepts are the things that are important to get so you can work the actual practice problems. All right, so 6, a positive particle is placed a certain distance away from a positive stationary charge, and then we do the same thing. So it's the exact same, whoops, don't knock things over. Yeah, we're going to get rid of all this. So here we do the exact same problem, except this now becomes a positive charge. And what happens? I believe it's exactly the same. I forget which number we're on. We're on 6 now, right? Yes. So yeah, exactly the same questions. Does it experience an increase or decrease in potential energy? Now we have positive times positive, so this is going to be a positive, small, because it's far away. It moves closer in. It's going to be a positive, larger number. So this is where we're going from a positive small to up here, which is a positive larger. So think of it, up the hill. So the potential energy actually increases in value, in the amount of energy that's there. All right, 7, a negative charge is placed near a stationary charge. Cool. And I'm guessing it's not going to tell us whatsoever what the charge on that other thing is. We'll get rid of all of this. Yeah, I need to find a better eraser next week. So we've got a stationary charge. We have a negative charge placed near it. If the electric potential is positive, so V equals positive, is the stationary charge positive or negative? Positive, positive. Are you positive? Absolutely. All right. It has to be positive because the potential is, and it's the electric potential. Yes, electric potential has nothing to do with this. We don't even need a negative charge there. Doesn't even matter what the charge is. If the electric potential is positive, the stationary charge is positive. That easy. That's all you have to worry about. And they don't even have a follow-up question there. So the negative charge was a red herring, something you should have learned to, by now, disregard. Number 8, a negative particle moves from the negative plate of capacitor to the positive plate. So we've got a capacitor going on here. Let's do a capacitor. 2 parallel plates, and we'll attach the wires off there. Let's do the positive plate up here, the negative plate down here. A negative particle moves from the negative plate. So we've got a negative particle, and it's going to move from there to here. Notice I don't have it jump across. Negative part moves from the negative plate to the positive plate. Is the change in electric potential positive or negative? And does the potential energy increase or decrease? Actually, I guess I should probably draw this. Increase or decrease. That might be a better way to do it. Where are we at on this? Can't tell timestamps on these. I guess is the decrease is the potential energy. And we have a positive, or is that from the previous question? Now I don't know which question's which. Oh my gosh, too many positives and increases and negatives and decreases. In the chat, if y'all could please put the question number we're working on, which is now number 8, with your answer. That will help me dramatically. So when the particle moves from the negative plate to the positive plate, its change in electric potential is positive because it's going from down in the valley to up on the mountain. All right, cool. So the change in electric potential is positive. The potential, to get the potential energy, however, you need to multiply by the particle's charge, which in this case is negative. And since the charge is negative, the potential energy is negative, so the potential energy decreases. Does that make sense to everyone? So if this is going uphill, but since it's a negative particle, going uphill makes it negative. All right. Let's see. Julie Andrews, Sound of Music. The hills are alive. Yes. Okay. She's running up the hill. She's a very positive person. That's an increase in energy. However, if you take a negative person and you try to make them climb up the beautiful mountainside, they're probably going to be getting more and more negative with their energy and dragging their feet. Does that help it cement in your mind? Does that work for you? For those that aren't as mathematically inclined and might be more artistically inclined, shall we say, you can do Julie Andrews with that one as your example. So number 9. Move on. Draw the path of the electron beam as it passes through the capacitor drawn below. Assume the charge stored in the capacitor is pretty large. Not ugly large, pretty large. I can't draw pretty charges, so I'm just going to draw a bare capacitor here. So we have a capacitor. I'll draw a rather large gap here. We've got positives on the top, negatives on the bottom, and we have a beam of electrons coming through. And for those that are chatting, I'm going to say drawing, it's either going to go bend up, go straight, or bend down would be your options. So it can either bend up, it can go straight, or it can bend down. So that helps with not having to draw in a chat room. And yes, the correct answer, as I've already got some answers, is it is going to bend up. And that is because the negative charge is going to be attracted to the positive, opposites attract, so it's going to bend up towards the positive. It's also going to be pushed away. So even if that wasn't there, it's going to be pushed away from the negative. So both ways you look, it will bend upwards. Number 10, final review question. Oops, hang on a second as I check. 1222. Why are there 3 beams of electrons in a color television set? And again, this book is getting quite dated because there aren't any. And that smart aleck answer, while maybe technically correct, will not get you the points on a test should it be asked. So why would there be 3 beams of in a color television set, and how many beams would you expect in a black and white television set? You want to go in the chat on this one. Each beam for a pixel color, that works for me, red, green, and blue. So yes, if you look at a TV set, or like the old school CRT color television set with a magnifying glass, so you can focus all that radiation right into your eyeball. You will notice that there are 3 little, there are rows, and I'm kind of exaggerating this a little bit, and I'm not using my colored markers. This one has a mustache. Okay. With red, green, blue, red, green, blue, red, green, blue, red, green, blue. And so as that beam scans across row to row to row, across each row, like we talked about in the last week, each beam's going to hit either the red, the green, or the blue and light it up, and possibly light it up by different amounts, different intensities. And so you get red here, red here, red here, red and green, which will give you, I forget now with the light versus pigment, because it's not the same as what you think going. I'm always used to pigments. Anyway, so you get the combination of colors across the whole thing. Black and white, you just have on or off dots, black or white. And so maybe you have, you know, ones not being hit and, you know, ones that are being hit. Cool. So any questions on the review ones before we get into the oh so fun practice problems? All right, let's get our algebra on. All right. Hold on a second, gotta flip back to where we're at. 14. All right, so what is this? Plus 2.3 millicoulomb charge is placed 35 centimeters away from a stationary charge. If it experiences an electric potential, I'll put it over here. If V is equal to minus 4.6 times 10 to the 7 volts, what's the value of the fixed charge? All right, so again, let's put these out to the side. So we've got Q1 equals plus 2.3 millicoulombs. I'll go ahead and do the conversion up here. So that is 2.3 times 10 to the minus 3 coulombs. We'll have enough space. We have a voltage of minus 4.6 times 10 to the 7th volts. We have an R equal to 35 centimeters, which equals 0.35 meters. And we are looking for Q2. Mark that off so that we can tell what we've started with and what's part of all of our working through things. This is obviously just a straightforward application of our main equation here, which is that, actually, wait, oh, yeah. K, Q over R. So you should see very quickly that I don't care about that. Doesn't matter. Doesn't matter whatsoever. It's thrown in there to throw you off the scent. Wait, we have V. We need to rearrange this equation a little bit. Let's multiply both sides by, we want to get what? Q. I'll even label this as big Q now that we know what we're dealing with. We need Q on the side, so I multiply by R over K. R over K on both sides, so those will cancel. We're left with Q. We end up with Q equals V times R over K, which is going to equal minus 4.6 times 10 to the 7th volts times 0.35 meters divided by, what is it, 9 times 10 to the 9, right? Making sure, oh, yep, top of the page. There we go, yep. Newton meter squared per coulomb squared. So Newton meter squared per coulomb squared. Great. What are we going to end up with on here? We're going to end up with, oh, first of all, we should probably make sure all our units work out right. So what we're going to end up with here is a volt times meter over Newton. Whoops, that's not a good Newton. Newton meter squared, and then divided by coulomb squared flips that coulomb squared back up onto the top. Well, those cancel. We need to figure out newtons and volts are going to get us some problems. So let's figure out what a volt is again. Anyone remember what a volt? Oops, hold on. Oh, yep, got the render stuff. Cool. So newtons we know are force, which is mass times acceleration, which means we know this is a kilogram meter per second squared. Volts, anyone have that one handy? I don't remember it off the top of my head. Oh, we can figure it out though, can't we? That's what, coulombs per meter? Ah, no, I've lost it and I don't have my book handy. Where's my book? I don't have my book handy. All right, someone quickly in the chat. What's the basic units for volts? It's Newton meter per coulomb. That's right. Okay. And this is going to be a Newton, or actually, so we can probably even leave that alone. That's a Newton meter per coulomb. So that coulomb is going to cancel that one. That Newton meter is going to cancel that Newton meter. And we're going to be left with just coulombs. So, hey, that's charge. Beautiful. All of that works. Good double check on things. Also make sure we understand what our units are made of. So calculator, phone. There's the calculator. So we've got 4.6 exponent 7. We've got 0.35 times. We've got 9E9 divide. I'm going to end up with 0.0018 coulombs, or 1.8 times 10 to the minus 3 coulombs, or 1.8 millicoulombs. Any of those three are probably correct. Millicoulombs is probably the most correct, if that helps. Yes, beautiful answer there, Drex. Awesome. And dancing doodles. And yes, those are the only ones that give me answers. So cool. Awesome. Let's see. Where else are we at? Okay. Next. And is that the answer they got in the book? That is the answer they got in the book. Awesome. Number 2. Let's get rid of this one. I hope. Yep. Totally different problem. Making sure we didn't have a follow-up problem that I wanted to leave something here for. And we don't. Two, in a 3.4 times 10 to the third volt potential, a particle has a potential energy of minus 12 joules. What's the particle's charge? So I'm not even going to draw a picture here, but I am going to say that the potential is 3.4 times 10 to the third volts. That's not minus third, that's 10 to the third volts. Potential energy is going to equal minus 12 joules. What's the particle's charge? Well, I think this is also a straightforward application of an equation we have, which is potential energy equals QV, if I remember correctly. We are looking for Q, so Q is going to equal potential energy divided by V, which is going to be joules divided by volts. Ooh, we should probably figure this one out. Is this going to work right for our units? Again, this is an analysis that's good to get into the practice of doing. I'm going to walk you through this because if I don't remember any of these things again, like before, let's see what we can do. Joules is energy. 1/2 mv squared is energy. mgh is energy. You know, so whatever. So that's, I'm going to do the 1/2 mv squared. So mass times velocity squared. So that's going to be a meter squared per second squared, right? M velocity squared. It's also going to be a mass times g, which is meters per second, times another meter's height. Okay, so those are the units for joules. Volts, again, we had, that was what, newtons per coulomb? Newton meters per coulomb, that's right. So that's going to be a Newton meter per coulomb. Well, let's take a look. Actually, we didn't even have to go this far since we had Newton meters per coulomb. Energy is going to be, work is force times distance, right? Force times distance. Work is putting energy into a system. So there we go. So the Newton meters cancel. We have 1 over C, which is going to be coulombs. So we're working out right here too. This also helps you figure out how to figure out the units in addition to making sure simple algebra is actually correct. So this will end up giving us numerically coulombs. So minus 12 joules over 3.4 times 10 to the third volts. Again, simple plugging into the calculator should end up giving me, I don't need a phone, come on, calculator. 12, enter, 3.4, E3 divide, and we get 0.0, well, I'll go right out, 0.0035 coulombs, which is 3.5 times 10 to the minus 3 coulombs, which is 3.5 millicoulombs. Again, all three are technically correct answers. The one at the bottom is probably the simplest to write, and thus is more correct most of the time. Number 3, a minus 5.1 millicoulomb charge that is free to move is placed 2.2 meters from a stationary charge. If it moves to a new distance, what's the change of potential energy? Did the potential energy increase or decrease? All right, so let's draw this up here. So we have a free to move charge that is minus 5.1 millicoulombs. We're going to put it next to a really big charge. Well, slightly larger charge. 2.20 meters. Stationary charge is plus 5.8 millicoulombs. If the freely moving charge moves 2 meters towards the stationary charge, which means it is now located, how am I going to draw this? Here. I'll put a plus and a minus here so I don't have to rewrite those numbers. It is now 0.20 meters away. Be careful on this one. Just because it has 2.00 meters there does not mean it's 2.00 meters away. It is moved that far towards the stationary charge, at least that's how I'm reading it. What is the change in potential energy? So we want, let's see, we've got Q1 equals minus 5.1 millicoulombs. I'll just say little q. Big Q is plus 5.8 millicoulombs. R1 is 2.20 meters. R2 is 0.20 meters. We want to know what the change in potential energy is. And is that an increase or a decrease. So there's a couple of ways we could go about doing this. One, which may be the way you start with. First of all, let me see which way the book does, because I think I'm going to do it a different way. Nope, actually, they do it the way I was going to do it. So one way that you could do is you could calculate the potential energy here, and then you could calculate the potential energy here. You could subtract one from the other, and then see whether it increased or decreased. That's an okay way to do it. It's probably not the way you need to get your mindset to going to do it for like the test. So what we're going to do first is, because the equation that we have, I believe, if I remember correctly, is the change in potential energy is equal to Q times the change in the voltage. So with that in mind here, let's work it this way and let's find out what the change in the potential is. So in that case, we're going to figure out the potential in the first case, which is going to be KQ over R1. We're going to figure out the potential in the second case, which is KQ over R2. And then we're going to subtract one from the other to get the change in potential. So in this case, we're going to have 9 times 10 to the 9th, what is it, Newton meters squared per Coulomb squared, times 5.8 times 10 to the minus 3 coulombs. Don't forget to change those units there. Divided by 2.20 meters. In the second case, we're going to have 9 times 10 to the 9th Newton meters squared per Coulomb squared times 5.8 times 10 to the minus 3 coulombs over 0.20 meters. Now, if you don't want to plug in all these numbers into the calculator, you could have done, and I'm going to kind of do both at the same time, whoops, delta V, let's isolate that, is going to equal V2 minus V1, which is going to equal KQ over R2 D2 minus KQ over R1. Are those still legible? I hope those are still legible. Doing a little algebraic trickery, we can pull the K and the Q out and have 1 over R2 minus 1 over R1, which means we only have to type those big long numbers in one time with the delta there. End result being 99.5 times, or 5.8 times 10 to the minus 3 times. So that big number across the top, I'm getting 52,200,000, or 5.22 times 10 to the 7th. We're going to multiply that by the 1 over R2 minus 1 over R1. So we're going to have 2.2, oops, nope. It's going to be 0.2, 1 over, enter. We're going to have 2.2, 1 over, minus. And so this thing right here is going to be 4.5454545454. We're going to multiply those together, and I'm going to get a nice repeating number, but we are at 2 significant figures. So I'm going to say that that is going to be 2.4 times 10 to the 3, 4, 5, 6, 7, 8. And that is going to be volts. Is that right? That seems really, really big. Initial, final, there we get the change, 2.4 times 10 to the 8 volts. Hey, look, awesome. So that is our change in potential energy. And that is a, hang on a second, make sure that's a positive number, R2 is smaller, so it's going to be larger minus a smaller number. So, okay, so it's going to be a positive change in potential energy, or sorry, change in electric potential. 1.2 times 10 to the 6 joules. Was that the previous one, or is that, nope, that's current. So you're talking a change in, wait, potential. Wait, we're looking, oh, that was potential. Now we have to multiply it by the Q. Got it. You were giving me joules. So Q is minus 5.1. So we're going to take Potential energy, is it still visible? Yes, good. Equals minus 5.1 times 10 to the minus 3 coulombs times this 2.4 times 10 to the 8 volts. And we're going to go, let me clear this out so I don't have, so I can get all the good rounding errors that we need to get. E8 enter and 5.1 E3 minus times. I'm going to get minus, actually I get minus 1.2 times 10 to the 1, 3, 4, 5, 6 times 10 to the 6 joules. Oh, nope, that's what you got, 1.2. Got it, yep. I was thinking 6. That does look correct, Drex. Yay, awesome. Very cool. If anybody has questions on this, wants me to slow down, back up, whatever, please, please, please unmute yourself and jump in. Catching things on the chat's a little hard for me while I'm actually working it out. Hey, we did problem 3. On to problem 4. I assume y'all can unmute and actually talk, right? They don't have a restriction on there for y'all not being able to unmute. I think I heard someone talk earlier. Someone want to give that a test real quick for me?
Meep.
Mimi, there we go. Cool. Wile E. Coyote would be proud. Please, please, please tell me that your parents educated you in the ways of the Roadrunner. All right. Where did I say? Number 4, a charge travels from the negative side to the positive side of the battery. If it started from rest, what is its speed when it reaches the positive side of the battery? Oh, awesome. So I get to draw my battery. I can actually do a fairly decent battery. It travels from the negative side. So this is a 1.5 volt battery. This is minus, this is plus. It travels from here up to here, and the charge is Q equals minus 6.5 millicoulombs. Its mass is equal to, actually I saw that Q looks like it's 0Q. That's not 0Q. The charge is up here then. Here we go. The mass is, holy moly, that's tiny, 0.0015 kilograms. 1.5 volts, started from rest, so V naught equals 0, V final equals, let's find out, shall we? Cool. So what are we going to find out? Anybody want to give me a real quick, what are we looking at here? Just a quick high level rundown. It's like pulling teeth on a cat. That was for your sake, Drex. Oh, sorry, which one are we doing? We are doing, this is problem number 4. I'll try to put that up in the corner if I remember. Number 4. So we've got a particle. It starts at rest. Negative particle starts at rest at the negative end of a battery, a 1.5 volt battery. It's not moving. It travels to the positive end. How fast is it moving when it gets to the positive end of this 1.5 volt battery if this is its mass and this is the charge on the particle? Someone want to jump in and verbally, just real high level, no numbers involved necessarily, just what are the thought processes going through the head?
So if we're trying to solve for the velocity, then we need to find the kinetic energy by using the kinetic energy equation, 1/2 mv squared. And the way to find the kinetic energy is to find how much we lost in the potential energy. So that it's the change in potential energy.
Something like that?
Yeah.
Cool. Very, very good. So yes, correct. So at the beginning, at the end, it doesn't matter what the potential energy is here and what it is here. We just care about the change in the potential energy. And the change in potential energy is going to be equal to essentially the change in the kinetic energy. Now, so technically, I'm going to get a little bit, you know, pedantic here, I guess, is going to equal that. But since the kinetic energy at the beginning was 0, because they said it wasn't moving, that makes this just equal to kinetic energy at the end. So this would be kinetic energy final minus kinetic energy initial is going to equal potential energy final minus potential energy initial, but we've already kind of got that in our equation, so I don't have to worry about it. And since the initial is 0, we can just say that 1/2 mv squared is equal to Q delta V. Well, what information do we have? We have that delta V equals 1.5 volts. We have Q is equal to minus 6.5 times 10 to the minus 3 coulombs. We have that M is 0.0015. That bothers me with scientific and non-scientific notation mixed together. And velocity we don't have, but we have everything else, and that's the thing we're looking for. So you know what? We've got this. Let's go ahead and solve this before we start plugging in numbers. So I'm going to multiply by 2 over m. So that those will cancel. We will have v is going to equal the square root of 2q delta v over m. I guess I didn't go that far, did I? Which is going to equal the square root of 2 times minus 6.5. And this is, I write this out because this is what I want y'all to get used to seeing for when you're doing things on a test. Delta V, oh good, nice easy number, 1.5 volts over a mass of 0.0015 kilograms. Oops, and I realize our V's and our delta V's, we need to be careful here. We're using big V's and little V's, not that you can tell on the board. Please be very careful with that when y'all are doing your problems on your tests. We have 6.5, and actually here, we don't need to worry about the minus sign there because it's 6.5 times 10 to the 3 minus times 1.5 times 0.0015 divide, I get 13. So the square root of 13 is 3.6. Is that the answer they got? Meters per second. Let's see, what are we doing before? 3.6 meters per second. Awesome. Yep. Very good. Everyone understand the concept on how we did that as well as the mechanics of working through it. If you can get the concepts of how we do something as well as the mechanics of working through it, you will do fine. And I must admit, y'all are doing much better at not being chatty today. How many parents griped at you ferociously during the past week for that, whether it was you or not? What's the parents? More of the email. Yeah, there's that. Well, I appreciate y'all's self-control today. We are on number 5, I believe now. Which we're done with that one. 5 out of 10, cool. A 1.5 coulomb charged particle mass is placed this distance from a stationary charge, starts to rest. How fast will it be traveling when it's 2 meters away from the stationary charge? Awesome. So we have charge plus 1.5 coulombs. Don't have to convert that one. The mass on that charge is 42.3 kilograms. Wow, that's kind of heavy. That's also a lot of charge. R1 is 1.4 meters. Stationary charge, I'm going to do as a big Q, is plus 4.4 coulombs. That's also a lot of charge. V naught equals 0. VF, we don't know, but R2 is going to be 2.0 meters away. There's the problem. So essentially we have a big charge. We have a small charge that's 1.4 meters away. That's Q. That's Q. When it is 2.0 meters away, V naught equals 0. What is V? And we can see they are both positive charges, so this will be repelling away, so it will be decreasing in potential energy as it goes away, which means that potential energy will convert into kinetic energy, so we'll need to figure that out. Again, probably a couple of different ways we can do this. We can calculate the potential energy here, the potential energy here, that change is equal to the kinetic energy, and then do the problem like we did before. Or probably the way the book wants us to do is to calculate the potential here, regardless of what the charge is, just because of the stationary charge. What's the potential? What's the potential? What's the delta V? And then the delta PE is equal to Q delta V. And I'll write all that up in a minute. Let me just double check that is indeed where they're going with this, because I have not been turning the channel in here. I'm 5. The delta V, yes, so that's what they're doing. Cool. So potential energy 1, or sorry, the potential in state 1 is going to be KQ over R1. Let's see, can I do this? Yeah, you know what? I'm going to do this really nasty algebra, and then I'm gonna plug all the numbers in, I think, unless it gets really nasty. So you can definitely calculate this as a number. Calculate V2, which is KQ over R2. Calculate that as a number. Subtract the 2 to get delta V, which is going to equal V2 minus V1, which is going to equal, and I'm going to go ahead and do the, well, I'll take the little steps. KQ over R2 minus KQ over R1, which is equal to K times big Q times 1 over R2 minus 1 over R1. All right, so that's our delta V. If we plugged in the numbers there, we should get the same thing as if you subtract things there. Now we've got the delta V, we really need, working backwards, like we done the last problem. Let's see. The change in kinetic energy is going to equal the change in potential energy, which means kinetic energy at the beginning is 0. Therefore, 1/2 mv squared is going to equal the change in potential energy, which is Q delta V. That's going to be Q delta V, right? And then we'll do the math later. Let's work towards the middle here. So we've got delta V. Actually, no, let's go ahead and leave it. So we've got the delta V. I should probably move this further up. I'm going to kind of draw a dotted line because we've got change in venue. We've got the change in kinetic energy equals the change in potential energy, which really means that the kinetic energy final is going to equal the, change in potential energy, I'll go ahead and finish it out here, is Q times delta V. That's one of our equations right there. So this is going to equal Q delta V, but this is going to be 1/2 mv squared. Doing our rigmarole math thing again, where we multiply by 2 over m on both sides. 2 over m times 2 over m. Cancel, so we have v squared. So we're going to have that the velocity is going to equal the square root of 2q delta v over big V over m. Well, delta V is this. So if you want to plug all the numbers in really nasty, we can have square root of 2q over m times delta V, which is, I'm going to rewrite this, k Q times 1 over R2 minus 1 over R1. Did everyone follow that? Yeah, that threatened with expulsion is a bad thing. Okay, so I just plugged the delta V from here in with our 2QM delta V that we had even derived from the previous problem we were working. Now we plug all the numbers in. That's going to be, screw it, 9 times 10 to the 9th, and that is what, Newton meters squared per Coulomb squared. Q is 1.5 coulombs. Big Q is 4.4 coulombs. I'll go ahead and do the mass. 42.3 kilograms. Good. We're still kind of in our standard units here, which is good. All of that, put it that way, times 1 over, what is R2? 2 meters. Minus 1 over R1, 1.4 meters. Now you just have to remember all your order of operations from standard mathematics stuff. I think I'm going to do this one first because it's the most complicated scenario here. So 1 over 2 minus 1 over 1.4. Wait a minute, how's that working? Oops, nope. Is that right? Final minus initial? I'm getting a negative number in here. That's not a good thing. Oh, positive minus signs. Okay, that's the other thing here. It's not really going to matter positive, negative here to a degree. It does matter, but to a degree, it's the change. So what is the difference? And we would have seen this over when we did it here. So really it's, you can think of it as for those of you that are familiar with the absolute value bars, what's the change in the distance there? What's the change in the potential there? So I get a 0.2143 out of that part. Now I'm going to multiply it by 2. I'm going to multiply it by 9e9 times. I'm going to multiply it by 1.5. I'm going to multiply it by 4.4. I'm going to divide it by 42.3. And I've got like 601 million something. And then I take the square root to get 2.4 times 10 to the 4th meters per second. Really? That doesn't seem right. I think I messed up somewhere. Oh, wait, that's problem 6. Nope, 2 times 10 to the 4th. There we go. They only kept it to one significant figure. That annoys me because they've got 2, 2, 3, 2, 2. All right, so the book wrote its answer as 2 times 10 to the 4th meters per second. Here's an example of where the teachers know if you're cheating and just getting the answer straight out of the book because the book didn't do it right, right? Cool, awesome. All right, so where are we at? Number 5, hey, 5 out of 10 problems, we're halfway there. Living on a prayer? Just wondering how many of your parents taught you right. Man, teaching in silence is like really hard for an extrovert. 6. Charged particle is placed so far away from a stationary charge. If it starts out at rest, how fast? This is the exact same problem that we've done before. All right, cool. We should know how to do this. So we have a charged particle. Q is minus 9.2 millicoulombs, which is minus 9.2 times 10 to the minus 3 coulombs. Mass of this charged particle is 3.5 kilograms. It is placed, so I'm going to say R1, 75 centimeters, which is 0.75 meters away from a stationary, big Q, charge of plus 2.5 millicoulombs, which is plus 2.5 times 10 to the minus 3 coulombs. Starts at rest. How fast will it be going when it has traveled? So delta R, 25 centimeters. Now I'm going to say there's a level of complexity here they may or may not have dealt with. Let's see. Change in potential. They don't address it, but they do deal with it. So again, same type of problem. We got to get to the kinetic energy. We've got to do that by a change in potential energy. Let's draw this out a little bit. So the big stationary charge is positive. The little charge is negative. They only tell you how far it changed. They didn't tell you what it was before or afterwards, right? So you got to figure out, is this going to go from 75 centimeters to 100 centimeters, or is it going to go from 75 centimeters to 50 centimeters? And so that's the trick that they're adding into this problem that makes it a little bit different than the one before. You know, they're trying to stair step you up with small steps here. Since they are opposite charges, I hope you will realize that opposites attract, and therefore this R2, and I'm actually just going to go ahead and write it here, R2 is going to be 50 centimeters, 0.50 meters, and then we'll draw the box around there. And because I'm OCD. So that's the extra little trick that gets added here. So let's figure this out. First of all, we need to figure out, let's go backwards. Actually, yeah, let's go backwards. Let's say change in kinetic energy is change in potential energy, just to kind of drive this home again, which is going to be kinetic energy final minus kinetic energy initial, which is going to equal change in potential energy. Well, that's Q delta V here. So that's Q delta V. But initial kinetic energy is 0 because its velocity initially is 0. Kinetic energy final is going to be 1/2 mv squared, which is going to equal Q delta V. Well, hey, look, let's, we're searching for V. So let's go ahead and solve for that. We're going to have an equation which should start looking really familiar, even if they never gave it to us in the book, which is going to equal 2Q delta V over M. Awesome. And no, you can't just pull that out of the thin air on the test. You're going to have to like work through it. So get used to working through it. Just so that the graders, AKA your parents, know exactly where you got it from, because they're never going to see that like anywhere probably. Delta V though, what is delta V? Where can I do this? Yeah, we'll work it over here. Delta V is going to equal VF minus V naught. Yeah, we'll do it this way. Voltage, sorry, the potential is going to be K big Q over R2. So this is actually final minus initial is going to be 2 minus 1. So KQ over R2 minus KQ over R1. Again, doing our lovely, actually, I'm going to do it down here. That's going to be KQ 1 over R2 minus 1 over R1. All right. We plug that up into here, and we're going to have our velocity is 2 Q KQ. Not the best way of writing that. I always like to have the constants 2 and K first and then the QQ. We'll put the M down here, and then times 1 over R2 minus 1 over R1. Stretch. All right. So there's our velocity. The trick on this one was just, again, figuring out what R2 was going to be. Was it going to be 1 meter or was it going to be 50 centimeters? So in this case, I'm going to come back all the way down here. And I'm going to say that V equals the square root of, and I'm going to rearrange the order here, 2 times 9 times 10 to the 9th Newton meters squared per Coulomb squared times Q, 9. And again, I'm not worrying about the signs here because we've already got the signs taken care of with the other stuff. 9.2 times 10 to the minus 3 coulombs times big Q, 2.5 times 10 to the minus 3 coulombs over mass. M's and meters and masses all also can get confusing. So 3.5 kilograms times 1 over 0.50 meters minus 1 over 0.75 meters. All of that square rooted. Plug it into the handy dandy HP calculator, fake on my phone. 9E9 times 9.2E3 minus times 2.5 E minus times 3.5 divide. Oh yeah, let's get the, so 1 over half, that's 2, 0.75, 1 over minus, and times. I am getting, and let's see if we got the right answer. I'm getting a velocity of 7.9 times 10 to the 4th. That should be meters per second. Let's see. Coulomb squared, coulombs, over meters. That gets rid of 1 meter. And we get rid of a kilogram. Well, so we end up with Newton meter per kilogram. But a Newton is a kilogram meter squared per, or sorry, Newton is mass times acceleration, kilogram meter per second squared, times a meter gives us that, divided by the kilograms, we'll end up with meters per second, meter squared per second squared here, square root, we get meters per second. So cool, we did it all right again. So let's see, what did the book get? Did I get it right? Oh, 280, yeah, probably so. I think I saw that too, yep. So something went wrong here. What went wrong? Let me see. And did I just do something wrong in the, is my equation right? Or is my calculator wrong? Where are we at? Let's try it one more time in the calculator. I'm gonna go backwards. I'm gonna go 0.5, 1 over, I'm gonna do 0.75, over subtract it. I'm gonna multiply that by 2. I'm gonna multiply it by 9 times 10 to the 9th. I'm gonna multiply it by 9.2 E3 minus times, I'm going to multiply it by 2.5 E3 minus times, I'm going to divide by 3.5. Oh, wait, and then I have to square root. Yeah, I didn't square root there. Correct. If you take 2.8 or 280 and you square it, you will get that answer. So that's V squared. Haha, V equals 280 meters per second. Cool. That's an example of where I got the wrong answer, did everything right, except I forgot to square root. So on a test, I would have lost a little bit, but not the whole problem because I had everything out there, right? Another lesson, another example. That just means I'm still human. I think this is too soft to erase. I will say these like microfiber cloths from Walmart are extremely soft and they can hold a lot of water in them. But you got to kind of rub and scrub with them because they're so super soft. They don't scrape this stuff off like they should. So there's your shopping tip. We are on to 7. We are at, oh, great, 18 minutes left, or more if I want to eat into the next class time. 6, right? 7. Charged particle mass shot with initial velocity toward, the particle starts out one, how close will it come to the charge before stopping and moving away? Okay, this one's cool. We get to shoot things now. So we've got a stationary charge of plus 1.5 millicoulombs. We have a cannon. Actually, I don't want my cannon that way. I'm going to do the cannon this way. That is shooting a charged particle. 3.8 plus 3.8 millicoulombs. Its mass is 5 kilograms. Initial velocity, 245 meters per second. Towards that. Starts off 1.2 meters away. How close will it come before it goes off? So picture this. We're shooting this object directly at it. Since they are both positively charged, as it gets closer, the repulsive force is going to get stronger and stronger and stronger. And so, okay, real world, you can't really nail these things down this far. But assuming physics la land, this thing can't move whatsoever. This gets closer and closer, the force gets greater and greater. It's going to start pushing back. I mean, it's already pushing back, but it's going to start pushing back very extremely, and then it's going to come back away. So we have to figure out how close is it going to get before it goes back, right? So this is kind of the reverse of the previous questions we've done. I mean, from a physics working problem, it's just the reverse of what we've done before. Instead of starting at rest and making it go, how fast is it going? We're going to start it moving and see when it comes to rest. So that probably just gave you a clue on how we have to work this problem. So we're going to start off with all kinetic energy. And we're going to find out when that kinetic energy gets converted to pure potential energy before it starts the reverse of the problem that we've already done, or starts the problem that we did before. So, you know, I'm just going to leave everything up there. This is R1. This is Q. And we want to know, I don't even know how to draw it. What's R2? So R2, where are you? Let's find out. Oh, come on. That was a good one. No reactions. See, extrovert teaching is hard via Zoom. Really, really hard. People don't understand the struggle. It's real. So initially, we have same equations. Actually, I'm going to flip these around a little bit. This case, the change in potential energy is going to equal the change in kinetic energy, right? Only in this case, we're going to have and actually, I'm trying to think if I want to do this the other way or not. No, we'll leave it this way. So this is Q delta V, but we're going to need to rewrite this too. We're going to have to expand on this side, which I'm trying to think. I guess we had to do it in the previous question. So here we have this is 0. So this is the thing that's we're looking at KE1. All kinetic to start with, no kinetic at the end. So here we're going to have Q times, remember the potential is KQ over R2 minus KQ over R1. That's going to equal minus 1/2 mv squared. In this case, there's only one velocity. We can do this V1 because V2 equals 0, and we don't have to worry about V2, and we'll just call it all V. and we want to find R2. That's what we're looking for, as always. So how do we get all of this over there? Well, we can simplify this a little bit. We've got Q, K, Q, and it may be easier just to work this out with the numbers, honestly, but I got to try and see if I can make it. Yep, no. To solve for this one, let's, no, we can't do it. Okay. This is going to be K, big Q, little q, times 1 over R2 minus 1 over R1. It's going to equal minus 1/2 mv squared. I'm going to divide by K, Q, Q, divide by K, Q, Q. So that all cancels. We end up with that. Actually, we'll put the 2 on the bottom there. We now have that. We are looking for R2. So we're going to add 1 over R1 on both sides. So we'll end up with 1 over R2 is going to equal mv squared over 2kq little q plus 1 over R1. Actually, there's a minus there. Don't forget the minus. All right. So really, if we wanted to write it, it'd be 1 over R1 minus mv squared. That's probably a simpler way. Oops, big Q, little q. All right, let's plug those numbers in. Let's slide this over here. And realize this is 1 over R2. So at the end, I need to reverse this. I'm just not going to do that because then it looks really nasty. 1 over R1, what's R1? 1.2 meters. Minus M, 5 kilograms, times V squared, which is 245 meters per second, all of that squared, divided by, oops, this is where I maybe end up out of room, 2 times 9 times 10 to the 9th Newton meter squared per coulomb squared times 1.5 millicoulombs, which is 1.5. These are both plus, so that's okay. Times 10 to the minus 3 coulombs times, I can't write this here, so I'm just going to write to the side here, times little q, which is 3.8 times 10 to the minus 3 coulombs. All right, we end up with coulombs canceling, so that's Newton meters times meters, that's kilogram meter meters second second, so everything's going to cancel out. We're going to end up with 1 over meters, which is what we want. And we should be able to do this. So let me clear everything first. Oops. Make sure I don't end up with, come on, clear. First stack, there we go. Woo, 5, enter. We have 245 squared divided by 2, divided by 9 times 10 to the 9th, divided by 1.5 times 10 to the minus 3, divided by 3.8 times 10 to the minus 3. Oops, and I need to put the other thing in. 1.2, 1 over, I swap them and then I subtract them. Wait, is this gonna work? I don't think I did this right. Hold on a second. Clear stack. Let's do 1.2, 1 over. We're gonna do 5 kilograms enter, 2.4 x squared times, that's a big number, 2 divide, 99 divide, 1.5 E3 minus, oh yeah, divide, I think I multiplied in there some, 3.8 E3 minus, divide, and then minus gets me a minus number. That's not right. Why am I getting a minus 2 there? We're on number 7. Let's double check. 1 R2 minus 1. That's plus. I wonder if I skip the minus. So let me try this with 5x squared times 2 divide 99 divide 5 E3 minus divide 3.8 minus divide. Okay, so all of this is coming out to 2.93 inverse meters. um, Yep, I think I messed up something somewhere by trying to probably put it all together at one point. The book is coming out with 0.27 meters away from the charge. Where are you at? So the book is coming out at 0.27 meters away from the charge. I may have tried to smarten myself up too much. Let me go back through. We got time. Yeah, we got time. We're going to do this anyway. Let's try this one step at a time and see if I can get it a little bit better, but with more numbers and more rounding errors. So if we assume that the kinetic energy at the beginning is going to equal 1/2 mv squared, that's going to be 1/2 5.0 kilograms times 245 meters per second squared. Ooh, did I square things? Maybe I didn't square things. 245 squared, 5 times 0.5 times. I'm getting kinetic energy is going to be 1.5 times 10 to the 5th joules. Okay, so that's got to go into potential energy. So the potential energy is going to equal Q delta V, which is going to equal, well, we already know this, right? Let me double check that's the way they're doing it too. Delta V, where are they calculating it? V initial. Okay, so they are calculating V initial and V final. Okay. Oh. Nope, that should still have worked out. Anyway, V initial should be K big Q over R1. We'll do V1. This should be 9 times 10 to the 9th Newton meter squared per Coulomb squared times big Q 1.5 times 10 to the minus 3 coulombs over an initial of 1.2 meters. Let's figure that one out. 99 enter 1.5 E3 minus times 1.2 divide. So the initial should be 1.1, we're doing 2 sig bigs, yep, times 10 to the 7th volts. V2 is going to equal, okay, so that's initial V. Actually, let's do this. QV1 multiply the Q. So we'll have the potential energy at the beginning. There we go. So potential energy at the beginning is going to be that. So we're going to multiply this by the other charge. 3.8 times 10 to the minus 3 coulombs. So we're just going to do energy, energy, energy. So 3.8 E3 minus times, which is going to equal So potential energy at the beginning is going to equal 4.3, rounding up, times 10 to the fourth joules. So we have kinetic energy at the beginning, potential energy at the beginning, and that's going to equal the potential energy at the end because there'll be no kinetic. So let's add these two together. That's going to be 1. So the total energy at the beginning, I'll just put E, is going to equal that plus that, which is 1.5 times 10 to the fifth plus 4.3, which is really 0.43 times 10 to the fifth. So that's going to be 1.9 times 10 to the fifth joules. That is the total energy before. We know that the potential energy at this endpoint is going to equal QV at the endpoint too, which is going to be Q, the potential is going to be, here we'll just write it all out, which is K Q over R2 times the charge. So we know if solving for R, divide both sides, we're going to have, and flip, we're going to have R2 is going to equal, divide both, K Q Q over the potential energy at 2, right? Yes. We have the potential energy at 2 because it's going to be all the energy turns into potential energy. So R2, and this may be something you want to go back and rewatch the video a few times now that we've got it figured out. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared times a Q of 1.5 times 10 to the minus 3 coulombs times 3.8 times 10 to the minus 3 coulombs over all of this, 1.9 times 10 to the 5 joules. And let's see what we end up with there, and let's hope it's the right answer. 99, enter, 1.5 E minus 3 times 3.8 E minus 3 times, and then 1.9 E5 divide, there we go, 0.27 meters. All right, so that was in some ways, probably a simpler way of going about it is total energy equals total energy. Here we have kinetic plus potential energy. Here we have just potential energy. Calculating the total energy before, we've got the kinetic energy, we've got the potential energy, electric potential energy beforehand, which is that. Over here, we have just potential energy, which is going to equal this. We solve for R. So that's the process. I'm not saying anything in the chat. I hope I didn't lose too many of you in that particular one. If you've got questions, let me work these last couple of problems, hopefully. And if y'all have any other questions, let me know, email me, text me. I can see if I can try to find another time to get online and answer some questions as well if there's people that need problems. It'd be nice if we could group that time into a single session though. Eight. What is the electric potential of a 3.2 micro, or 10 times 10 to the minus 6 farad capacitor when it stores 0.5 coulombs of charge? All right, so we need the electric potential. We know that the, totally lost it. What's our symbol here? 8. Oh yeah, capacitance. 3.2 times 10 to the minus 6 farads. When it charges or stores the amount of charge equal to 0.50 coulombs. Again, we get to a very simple one where it's a simple application of our equation of, all right. So that's going to be 0.5 coulombs over 3.2 times 10 to the minus 6 farads. Remember hold on a second, times C. That is going to be equal to, or a farad, sorry, is equal to, or Q, coulombs per volt. Okay, we got a new unit. So remember, that's our setup there. Since we're now using volts, coulombs, and farads, all things which are just things that are named after somebody else and don't make a lot of intuitive sense to our, brains that we've got. It gets a little harder to remember what those things are. So remember that one. And then we plug this into the calculator, and they get 1.6 times 10 to the 5th volts. 6 or 5th? Fifth. All right, so 8 should be fairly simple. Cool. I assume that was from problem 7 in the chat there, so. And number 9. That page done, 2 more. A proton, 1.7 times 10 to the minus 27 kilograms. Q is plus 1.6 times 10 to the minus 19 coulombs. That's actually a number that's not bad to memorize because protons are positive, electrons are minus, but it's that number. At the edge of a positive plate of a, let's see, what is this? Capacitance, 1.4 times 10 to the minus 6 farad capacitor. If the capacitor holds a charge of 2.2 microcoulombs, which is 2.2 times 10 to the minus 3 coulombs, minus 3, how fast will the proton be moving when it reaches the negative plate? We are now getting into the stage where we are basically putting everything together that we've all learned all the time on. So it experiences a change in electric potential. Let's figure out, remember, we did this before with changing electric potential. So let's, okay, ooh, hang on a second. So I'm going to say velocity, because that is not voltage. We're going to have some problems here with our V, so bear with us. V is Q over C. So the electric potential change that this proton experiences is going to be 2.2 times 10 to the minus 3 coulombs over 1.4 times 10 to the minus 6 farads, which is equal to 1.6, whoops, times 10 to the minus 3 volts. If I got that right. Oh, sorry, 10 to the 3. Minus 3, minus 6, the minus on the bottom, yes. Okay. 1.6 times 10 to the 3 volts. Now move, let's draw a picture. I'll do it down here just to make sure we got this right. So this is the positive plate, this is the minus plate, and we have a proton. And the proton is moving from, this is where you got to make sure we get everything straight. It starts up here, that's right. So it's a proton and it's going to go down there. So the fact that it moves from the positive to the negative one, it's a decrease in potential. It's going downhill. It's not a negative charge, which makes everything backwards. So it's a normal ball rolling down a hill. So the potential, the change in the potential is minus 1.6. So delta V is going to equal minus 1.6 times 10 to the third volts. So we use that to get that sign right there. Calculate the magnitude of the change, whichever way you go, but now we have to figure out whether it's positive or negative. So that's going to be important when you're taking the test. So now we get to the change in potential energy. That's going to equal Q delta V, which is going to equal plus 1.6 times 10 to the minus 19 coulombs times minus 1.6 times 10 to the third volts. Which is going to be minus 2.6 times 10 to the minus 16 joules. Okay, because volts is Newton meters per coulomb. So the coulombs cancel, we end up with a Newton meter is a joule. So that's the change in potential energy. The kinetic energy at the end is going to equal 1/2 mv squared, which is going to equal the change in potential energy. So we're going to have, let's do this. So that's going to be 1/2, let's not do it that way. Let's do minus 2 point, well, it's going to equal that energy. So the change in potential energy all gets converted in, so we don't need to worry about the sign there because it's going to be all converted over quantity to quantity. What's the best way to write this? Let's just write it all out. So that's going to be 2.6, did that before, 2.6 times 10 to the minus 16 joules. Solving, let's plug everything. Well, multiply by 2 over m times 2 over m. So we're going to have V equal the square root of 2 times 2.6 times 10 to the minus 16 joules divided by an m, 1.7 times 10 to the minus 27 kilograms, square root. We plug all that in. Two, 2.6 E16 minus times 1.7 E27 minus divide, get really, really big number, square root. And we're going to end up with 5.5, yes. 5.5, 2 digits, 2 single figures, yes, times 10 to the 1 to 3, 4, 5, fifth meters per second. Is that what the book got? 5.5 times 10 to the fifth? Yes, we're good. Awesome. Checking for questions. This was your favorite problem or the one before that? Number 9? So number 9 puts like almost all of this stuff together that we need to do. It is 141. We probably need to, let me see what the last one has anything new. Problem 10, the electron moves from the negative plate to the positive plate of capacitor. If it starts at rest, reaches a speed of this, how much charge is stored in the capacitor? So it's going to be the same thing, same problem, except we're solving for a different one of these variables. But let me go through the thought process, if not the algebra, to figure out, to make sure we've got everything right. So if we've got, I'm going to keep the positive plate on the top. It's just always easier to keep the same thing here. We now have an electron, which is negatively charged, and it's going to move. Okay, so a negative electron, and it's going to move from there to here. So this is where you've got to start thinking about the ball rolling up or downhill, and then whether it's a ball or an anti-ball. So in this case, we're going from the negative to the positive. So we are rolling it uphill, which you would think would increase the potential energy, except it's an anti-ball. So rolling an anti-ball uphill decreases the potential energy. In other words, all the potential energy is higher here. It goes to a lower value here, but it's still kind of the same thing. It's still all this potential energy being converted into kinetic energy here, and then the same equation we had before, except we are now figuring out the charge stored on it instead of the velocity. But that's where we're looking for that value instead. Does that work? Oh, it's back to 8. Okay. So does that work for everyone? So we can get off. I'm going to open up the last couple of minutes before they kick us off for the next class. Any questions anyone has on any of this? Does anyone feel the need for any sort of study session or for me to make myself available between now and when you need to take the test, which should be before Tuesday so your parents can grade it and get help grading it Tuesday night? Feel free to toss a microphone on if you need it, or chat in the chat window, either way. Okay, these recordings are available on the YouTube channel. I think that goes out in the email. If anyone needs anything, have you, your parents, whoever, email me, text me, and I will do what I can to make myself available via video conference for any of y'all. I will be online Tuesday at 7 p.m. on the Jitsi channel that I've got set up, that I've mailed out emails. I'll send another email out before Tuesday as well. So have a great week, people. Stay safe, stay well, wash your hands, and we'll see y'all next week.